All right, this is the conflicts passage. We know it's conflicts because it says scientist one, scientist two. It's usually going to say scientist or student or hypothesis. There's only one conflicts passage per test. Really important to decide when you're going to do this passage or if you're even going to try this passage. So in our DRC approach, conflicts means carefully read. You're going to spend more time in the reading on this one. You're kind of flipping the process. Spend more time in the reading, and then you're going to spend hopefully less time in the questions. You got to seek to understand the passage before moving to the questions. So there's one conflicts passage per test, and it's really trying to make sense of something you may not know. Think of it as open book science, so you're just trying to understand the differences in the hypotheses presented. So step one is to identify the conflict. Step two, identify the differences. So the conflict is usually in the first paragraph, usually this last sentence, but here it just says two scientists present their viewpoints. So the first part, first sentence, first paragraph says 4 billion years ago the sun was only 70% as bright as it is today, but the temperature was still well above freezing. Scientists believe that one of two greenhouse gases was present in the atmosphere at a condition well above the respective gas today. It trapped enough heat to keep the surface temperature above freezing. So I'm imagining the two scientists are going to talk about how those two gases went about trapping heat. Step two is to identify the differences. I'm a big fan of drawing on these passages. I think once you kind of draw it out, it gives you a better chance to understand what's going on. So I'm going to be modeling that. So let's just break this down, kind of like we would break down a question. So 4 billion years ago, large quantities of NH3 continuously entered Earth's atmosphere from ocean, floor, hydrothermal vents, and other processes. That other process is a little tricky. So I'm going to draw just an ocean and a floor with NH3 coming up. That tells me that that's where it's coming from. Next step, it's a more efficient greenhouse gas than CO2. So I'm going to underline NH3 and put CO2 in little writing. That's just my key to say, hey, this was more efficient. NH3 molecules entering the atmosphere would have been broken down, though, in 5 to 10 days by UV radiation. So I just drew a sun, 5 to 10. That's how long it takes to break it down. However, methane, CH4, another gas that was abundant in the atmosphere, combined with molecular nitrogen to produce organic compounds that blocked the incoming UV radiation. So I just did CH4, made a little arrow to combine, and I put a little shield right there to say it's blocking the sun. Continuous removal of CO2 from the atmosphere by the ocean prevented CO2 from accumulating in the atmosphere. So I'm just going to draw a little arrow down that says CO2 is being captured by the ocean. It's kind of nice that I drew it underneath the water also. Here's my actual drawing that I did on when I did the test. So it's similar. Now let's break down scientist two. Two carbon isotopes found in sedimentary rocks indicate 75% higher concentration of CO2 in Earth's atmosphere 4 billion years ago than the 360 parts per million today. So I'm saying CO2 equals 360 plus 75% of 360. Large quantities of CO2 continuously enter the atmosphere through widespread long-term volcanic activity. So I'm just going to draw a volcano spitting out CO2. Let's say CO2 is removed from the atmosphere and becomes part of carbonates and rock and sediment on land. However, 4 billion years ago, there was 80% less dry land. Okay, so I'm going to draw some land, draw an arrow with CO2 going into it, but 80% less dry land. CO2 accumulated in the atmosphere. The vast amounts of CH4 would be required to help preserve atmospheric NH3 did not exist. Okay, so CH4 and NH3 were too low. So there's my picture. Here's what my picture looks like when I actually drew it. So I just kind of try to model in my diagram what my picture looked like initially. Our next step of the questions is read and reread. So you're going to reread the question by breaking it down. That's what we're doing together. Which of the following diagrams is most consistent with scientist 2, this is scientist 2, of how CO2 enters the atmosphere? Well, from my drawing, from the reading, we know that CO2 enters the atmosphere through widespread volcanic activity. So it's going to come out. So we're going to eliminate G and H. And then it says it goes into the land. So we can see that in the picture and the reading. So choice F.
CH4 is also a greenhouse gas. Scientist 1 would likely agree that the presence of CH4 does what? So if you know it's a greenhouse gas, you know greenhouse gases generally help to warm the surface. But we also see from the reading that CH4 combines with NH3 to provide this barrier for the UV rays. So it definitely helps warm Earth's surface. So A. Question number 30, we're using scientist 2's viewpoint. Make sure you're looking at the correct viewpoint. A given concentration of NH3 can trap as much heat as 3 times CO2. Okay, so present day concentration of NH3 would trap an amount of heat equivalent to that trapped by present day concentration of CO2 would be approximately what? So present day CO2 is 360 parts per million. So we see in our answer choices, we have the ppm, parts per million, so we don't have to worry about that. No conversions. And we also documented that 360 in our drawing. So it's going to be 360 divided by 3 will tell us how much NH3 we need, which is 120, right? Or 3 times 120 would equal 360. Number 31, the sun was 30% dimmer 4 billion years ago than today, assuming the relative proportions stayed constant. So as one thing gets bigger, the other thing gets bigger. One thing gets smaller, the other thing gets smaller. Both scientists would agree the minimum total concentration of all greenhouses necessary to keep Earth's surface above freezing 4 billion years ago was, the answer has to be A, more than the concentration necessary today. Because all proportions stayed constant, the sun provides more energy to keep us warm today. 4 billion years ago, the greenhouse gases had to provide more energy. So A. It's a thinking question. Number 32 is a suppose question. So anytime you see suppose if Y, that is a key that is going to be some critical thinking involved. So suppose volcanic activity produced large quantities of CH4, which scientist would use this information to support his or her view? Now, we're going to look at both scientists. You might be tempted to say for sure, oh, it's got to be scientist 2. That's the one that has the volcano in it. However, if you look carefully, don't get tripped up by it. The scientist 2 says the volcano emits CO2, not CH4. In fact, part of the argument of scientist 2 was that NH3 and CH4 were too low in the atmosphere to have any real impact. So we're going to go to scientist 1, eliminate H and J, and now we're looking at scientist 1. It's either would explain how CH4 or NH3 entered the environment. Now it's a pretty easy answer. It has to be CH4 because that's what we're talking about being emitted by the volcano, and that's what also scientist 1 says. So your answer is F. Given unlimited time, it's a pretty easy question. Being rushed on the test, pretty hard question. Number 33, in order to protect NH3 from incoming UV radiation, the organic compounds had to be located where? So they're providing this shield, so they have to be above the NH3. So it's going to be at or above the elevation of NH3, so B. Number 34, scientist 2 would most likely agree that the concentration of Earth's atmosphere 4 billion years ago is closest to what? So we actually see in the reading that 4 billion years ago, it's 75% higher than 360. Our only answer choice bigger than 360 is choice J. So you don't even have to do the calculations. You could if you wanted to, right? 360 plus 75% of 360 is 270. So 360 plus 270 is 630. No need to do that. You got the answer just by knowing the concept. So J. All right, reach out if you have any questions. Here's the answers again if you need to take a moment to look at them.